right, let's go. Oh, I knew that was going to be off. You get to see some of my bookcase. All right, let's go. So this is the third lecture. Oh, sorry, I got to adjust this a little too. There we go. So this is the third lecture. We're on classes, and I've said it plenty of times. Is that okay? I've said it plenty of times. I'll say it at least one more time here. The summer moves extremely fast. After today's lecture, we will be 30% done with all of the lecture content for the entire summer for this 6 weeks. So let's jump into it and start learning some classes. Did this class 6 years ago in Scala, and every summer YouTube brings me back. Nice. Good old memories. And even though the course has changed quite a bit, it's in Java now, but at the same time, it hasn't changed all that much. Like a lot of the, what's up, Rue? A lot of the concepts are still exactly the same, and even some of the examples is the same examples, just in Scala. So yeah, should bring back some memories pretty robustly, pretty clear. All right, so let's jump right into some slides. And I always download the slides. I don't know, it's force of habit. It's overwriting the slides that just existed, but that's fine. I like to make sure I have the latest version of the slides. I don't remember when I make updates. All right, so presentation mode. Let's do it. Objects and classes. I don't think I have any announcements. Right, we are jumping right into it today. Yeah, I think we're on track with everything. Oh, I do have one announcement actually. I have office hours. So there are now 2 TAs. We were just going to have one, but we have 2 TAs on the schedule. 2 TAs for the course, and they have their office hours on the schedule now. So after each lecture, we do have office hours. Myself today, and on Thursdays it'll be Jack. Wednesday is Jack will have office hours, and Miriam has been very brave. We'll have office hours right before the deadlines on Thursday nights. So if you have your last minute questions and you're trying to get that assignment in before the deadline, Miriam will be there. I don't think this will stay as a 5-hour block. She might lower those office hours, but she's somehow brave enough to commit to the right before the deadline office hours. She wants to maximize the amount of help she can give y'all, and that's usually when students have the most questions. When you're panicked, you've already had a week to work on the assignment, and you're just stuck. Miriam's going to be there to help you out. And of course, answering questions on Piazza, we got that as always as well. All right, with that, let's jump into some content. So today we want to talk about objects. I know it says classes on the screen, but really what we're after is objects, and the whole lecture week is kind of called classes, but we've been working with classes all semester, which feels weird since we started 1 week ago. But we've been using classes in Java. We have to use classes if we're coding in Java because that's just how Java works. All your code has to be in a class. What we want to shift to today is using those classes to create objects. Because what a class really is like a recipe or a blueprint to be able to create objects. That's the main power of having classes. And so far, we've just kind of been ignoring that very major aspect of classes because, well, we just wanted to review the 115 material, learn how Java works, Java syntax, and everything before we get into a new concept. This is our first 116 concept. Last week really was just 115. None of that should have been new to any of you. You should have just, really blew through all that content, understood all of the concepts already, and just learned the new Java stuff, which is just honestly a little bit of syntax. Realistically, last week could be condensed into 10 minutes. Here's how you do things in Java. Maybe not, because we have to talk about strong typing. But this is the big new thing. This is 116 learning objective content starting right now. And we've seen this with array lists and hash map, and in 115 you see this in Python with lists and dictionaries, where we do actually create objects. whenever we're putting something on the heap and managing it through a reference, that is an object. Like, we're using an object at that point. So today we want to crack that open and talk all about how that works and what's going on there. So when we say new array list, whenever we use the keyword new in Java, what that means is we are creating a new object on the heap. Before we just said we're creating a new array list or a new hash map, but the general term is creating an object on the heap. And what we want to do today, oh, and by the way, I use this example because I sometimes don't get this example in otherwise, and last week I didn't get this one in. If you want to create an array list and initialize it to some initial values, so here I want to create an array list with the values 10, 9, 8, 7 in that order, and I don't want to create an empty array list and then call add 10, add 9, add 8, add 7. I don't want to do all that. You can use this arrays.asList method. Make sure you import the arrays class and call this asList static method from the arrays class. Give it a list of whatever values you want to add. It has to match the type of your array list. And as long as all that lines up, you can have an array list that's initialized to some initial values. But what we want to do today is create our own, at least for the first third of this lecture, I should say. I'm used to this just being a one-day lecture. But for the first third of lecture, what we want to do is create a class that is used to create our own objects of our own type. And that's what we're going to do here. So we want to create objects where we can say new whatever and be able to create objects of whatever type we define and create those objects on the heap and manage them by reference and all that stuff, all that goodness. And the example I want to do today is creating a player class. Think of a player in a video game. They're going to have 3 variables: their maximum hit points, their current hit points, and their name. So just 3 things that we want to keep track of with our object. And this is what objects are designed to do, is be able to control state and behavior. An object really is, I know it says class on the screen, classes and objects are very related, but an object is a container for state and behavior, which you can think of as variables and methods. So I have one package that's going to have all the variables and the behavior that depends on those variables all in one container called an object, and we're going to write classes to be able to define how those objects will behave. So here's my first syntax for my first class. I'm just going to throw most of the code at you right now, and then we'll break this down. We'll spend 10, maybe 15 slides, I think, on this code right here, breaking down everything that you see here so we understand all of this stuff, because there's a lot of new stuff. We see private, we haven't seen that before. This dot, we see this strange looking method with no return type. A lot of stuff going on here. We'll break it all down. But this is our goal, is to have one container for state and behavior. So our state here is max HP, HP, and name. Those are our 3 variables for this object, and then the behavior is any method defined in that class that defines the type for that object. A lot of words, a lot of kind of new words too. So let's break this down. Let's start going through it. So we have a class named player, so we are defining a type named player, or a class named player that's going to be used to create objects of type player. And we have 3 variables defined in the player class. What this means is any object of type player is going to have copies of these 3 variables. So if I want multiple players in my game, which is a big point of defining classes, if you want multiple objects of the same type. I want multiple array lists of the same, I want multiple objects of type array list in my code. I want multiple objects of type hash map. I also want multiple objects of type player. I want a multiplayer game. I at least want 2 players being able to play against each other, in this example at least. So I can create 2 objects of type player, and each player, we can call them player 1 and player 2 for simplicity. Player 1 and player 2 can both have independent HP. If player 1, say, attacks player 2, player 2's HP should go down. Player 1's HP shouldn't go down, though. They need their own copies of these variables. They need to maintain their own HP variable. And that's one of the big things we're getting with classes, is each object has their own copy of these variables. And these variables have a special name. I'm going to call them instance variables throughout 116. These variables have a lot of different names. It's one of those things where you ask 10 different developers, you'll probably get at least 5 different answers as to what do you call these variables. I'm going to call them instance variables in the context of 116 because I think it makes the most sense. It's more descriptive of what they are. They are variables that belong to an instance of a class, and an instance of a class is another way of saying an object of that type. So we create an instance of type player. That player gets copies of all the instance variables. You also hear them called state variables. I actually used to call these state variables. So when Learn with Salim took the course, I probably called them state variables at that point because they do control the state of the object. I think that does make sense. I switched to instance variables. They're also called fields, and I'll actually call them fields outside of 116 pretty often. I like fields because it's one syllable. It's just, I like the brevity of it. I don't like it because I don't think it's very descriptive of what these things are. Fields, it comes from mathematics. They call these fields for their purposes. They're equivalent of the same concept. And then we kind of borrowed that. So some people just call them fields if they're coming from mathematics, and it kind of spread and stuck. But I like the single syllable. But if I say these are fields, it's just a brand new word you have to learn. Instead of instance variables, they're variables that belong to an instance. Is more descriptive. And then also object variables. They're variables that belong to objects. I might start calling them this at some point because this is even more clear. You don't have to learn the word instance. But out there in the wild, you hear any of these terms and several other ones. They're all referring to the same exact concept, the same exact thing, variables that belong to objects. Yeah, when I say it like that, maybe object variable is what I'll start calling them. But instance variable, that's what I'm sticking with this semester. I like to pick one per semester and just use that term throughout the whole semester. This semester it's going to be instance variable. And then we have this very special method called a constructor. Now, I very briefly mentioned this last time. I said when we create a new array list or hash map, we're calling a method called a constructor, but don't worry about it yet. The only thing you need to know at this point is that it is a method call, so it needs a parameter list or an argument list, and that argument list was empty. That's why we needed the parentheses at the end of that call. And then I left it at that. That's it. That's all we need to know last Thursday. Summer moves so fast. It was just Thursday. 5 days ago. Today we need to know what a constructor is, and this is a constructor. This is a very special method with a very special syntax where if it follows these certain rules, then Java will treat it as a constructor and treat it as a special method. So the two big conditions for a constructor are the name of the method has to be exactly the name of the class, down to the capitalization, every single character. So this is these constructors are the only methods that we'll see that will start with a capital letter. Because our naming convention, classes should all start with a capital letter, be upper camel case in Java, and methods should be lower camel case, meaning if we start a new word, it's going to start with a capital letter, but lower camel case means the very first word is going to be lowercase. That's our naming convention for classes and methods, but this is a special method that needs to match exactly the name of the class, so it's the only methods that we'll see that will start with a capital letter, because they have to match the name of the class, which by convention needs to start with a capital letter. Strictly speaking, doesn't have to, but you really should, or else everybody, when you're working at a company, every one of your coworkers is going to get really mad at you if you don't follow the naming conventions. If you have lowercase class names, Java won't get mad at you, but the humans around you will, as they should. Programming is hard enough. We don't need to make the code harder to read unnecessarily. And the other condition is that there's no explicit return type for a constructor. So we have our access modifier, public in this case. We have the name of the method. Usually in between the two, we'll have the return type, int or void or double or whatever. With a constructor, we don't specify any return type. The return type for a constructor is going to be a reference to the object that was created. Like Java's going to handle that with the keyword new and everything. That's all going to happen behind the scenes. But we don't have to specify it. In fact, if you put any return type here, if you put a return type of player, for example, Java's going to be mad at you and say, hey, this looks like a constructor. You don't do a return type for a constructor. So just no return type specified in your code, but a constructor will, when combined with the keyword new, will return a reference to the object that was created. Like if you say new array list, you're getting a reference to the array list that was created. Same thing here, we're going to say new player, and then we'll get a reference to the player object that was created on the heap. So name matches the name of the class, and no explicit return type. Got those two things, you got yourself a constructor. Java is going to treat that method as a constructor. And then when we do want to create our objects, I'm going to say new, and then the method call for the constructor. So it's new, and then after the keyword new, it's just like any other method call you've ever seen in your life. There will be one difference when we get to the memory diagram. Actually, you can see it on screen right now. We're going to have this keyword this. That'll be a big new thing. We'll talk about that when we get to, well, I think it's the next slide actually. But we'll talk about it more and more as we go. But when you're calling the constructor, the big difference is the keyword new, and then everything else is a method call. The name of the method, which is player. We're calling this method right here, named player. It takes a string and an int as parameters, so as arguments, I have to give it a string and an int. So we have the name of the method, and then the argument list in parentheses, and give arguments matching the parameters, just like any other method call you've ever seen. So nothing new there, but it is a special method that will create an object with that information, with those arguments. And then what our constructor here actually does is initializes the state of our object. And that's the purpose of a constructor, is to set the initial state of an object. So all those instance variables need to be initialized. I shouldn't say need to be, but should be initialized by the constructor, because that's the constructor's job. You're going to want different objects with different initial states. The constructor is how you set that initial state. So I want two players. I'm going to give them different names, and maybe the human players chose different classes. Those classes start with different max HPs. Then I'm going to set that max HP in the constructor. You chose a mage, your max HP is going to be lower. You chose a warrior, your max HP is going to be higher. This is how we're going to set that initial max HP, is through the constructor. And then the states can change after the constructor is called. The player levels up, max HP goes up. Things can happen after that, but the initial state is set by the constructor. And in here we're saying the constructor as parameters does not have to take every instance variable. In this example, their HP is always going to start at max. Everybody starts at max health. What's up, Vibe Club Vids? I don't know why I struggle with that. HP is going to be set to max HP. So it's always starting, every player starts at full health. And then we see the keyword this. The keyword this is one of those really slippery topics. It's something I'll try to spend a lot of time on lecture and break it down. Every time it comes up, I'll give it a good explanation, including this time. The keyword this stores a reference to the object that called the method. This is the context of the method call. It was called through some object. This is a reference to that object. And in the case of constructors, it's kind of a special case. I need new wording for it. In the case of a constructor, it's a reference to the object that is currently being constructed. Now, if you fully understand that, you understand the keyword this, and we're done with that one. Historically speaking, this is a big point of confusion, so I'll spend lots more time explaining it. But that's the dry definition of it. This is a reference to the object that called the method, and technically, when a constructor is called, the object that called the method is the object that's being created. So this is a reference to that object. And then we use, just like our references to array lists and hash map, we're going to use the dot operator to head over to the heap. So this is a reference. We very, very rarely, if ever, care about a reference or the reference's value itself. What we care about is the object being referenced. So the dot operator takes us from a reference to the object that's being referred to. And so if I do this, that's the object that's being created. Dot takes me over to that object on the heap. And then I'm going to look for a variable named max HP, which is the instance variable max HP for this object that's being created. I'm going to initialize it to max HP from the parameter list. So here on the right hand side, I did not say this dot. So max HP is going to be the parameter. This dot max HP is the instance variable. I got two variables with the same name, which I did intentionally just to emphasize this point. To differentiate between them, it's either max HP parameter. This dot max HP dot takes me over to the heap, and I'm looking for max HP over on the heap at the object referred to by the keyword this. So that's what's going on with the keyword this. Again, I'll have many more explanations every time it comes up, especially in the memory diagram. I think the memory diagram's the best visualization. It's the best explanation of this because there is a visualization. I think it makes a lot more sense there. So that'll be the next place that I really explain the keyword this. And you do not, I just said the constructor is responsible for initializing the initial state of all the instance variables of your objects, but it doesn't have to initialize all of them. It doesn't have to be responsible for every single variable. If you, for example, want to hard code that every single player starts with a max 10 HP and starts at full health, you can initialize your variables in line like this. And often that saves some, you have fewer parameters in your constructor, just saves some typing, saves some coding, makes things a little cleaner, can be very useful. If some instance variables do not vary their initial state based on a per object basis, then you don't have to put that in the constructor. But the constructor is going to set anything that does vary on a per object basis. So I want each player to have a different name. I'm going to leave name as a constructor parameter so every single player can get their own personalized name, even though they're all starting at 10 HP. So in this case, I wouldn't have class selection, for example, in this game. This would be a different game, different feature. And I say, nope, everybody's the same class. Everybody starts at the same HP. And I'm going back to the non-inline. I just want to have one slide on that just to make sure we're all aware that exists. So if you want to use that, go for it. And then this guy. Okay. The keyword private. Let's talk about this. So in Java, our instance variables should almost, I'll put a little asterisk here, almost always be private. This is the Java way. We are coding in Java. We will do this in Java. This is another thing that I learned with Salim when I taught in Scala. Didn't see. There were no private instance variables in Scala. This is a Java-specific thing and a few other languages. It all depends on the architecture of the language itself, whether we use the keyword private here or not. For example, Python doesn't even have the keyword private. We didn't make anything private there, and there are good reasons for that. Python's built different. The way Java is built, we're going to use the keyword private here, which makes these variables inaccessible from outside the class. So we cannot access these variables using any code that's outside the braces that define the class. If we're inside the class, we can access these all day. I'm doing that right here. I'm accessing max HP, HP, and name directly and assigning those variables directly. I can do that because I'm inside the class. But once you're outside the class, which is where you're going to be, like if you're creating a game, you're not going to put your entire game code in the player class. It doesn't make sense. You're going to have some game class and game world and physics engine. You're going to have all kinds of different classes to separate all of your code for the different aspects of your game. In any of those classes, you cannot access these variables. So say you have your GUI, your front end to your game, your display for the human player, and you have your player objects, and you want to display the current HP in a health bar. You want to get HP and max HP and have some nice percentage and a nice health bar. You can't just say P1.HP and get the HP. You can't do that because it's private. Can't do that. Not allowed. And this is something we call encapsulation. We're going to hide the details of how our code works and then expose a public interface and make everybody go through the public interface to be able to work with the code that we're giving them, the code that they're using. Very, very important concept, encapsulation, to be able to hide the details. So nobody needs to know that we have these 3 instance variables, but we will expose a public API for them to be able to actually work with these variables. And for this, we use getters and setters. Anyone coming from AP computer science in high school, you've seen these, or anyone who's just had Java experience before this class, you've seen these getters and setters. This is the Java way. We will do this. Like I said, I taught this same exact course in Scala. I didn't talk about getters and setters at all. The same exact course in Java, I'm talking about getters and setters. I didn't change, but the language changed, and this is a Java, kind of a Java specific thing. But understanding the reasonings for this is, will just, broaden your understanding of programming, why we do this in Java, but not in Scala and not in Python. So let's talk about it. So we're going to make public methods called getters and setters. And this is how the outside world, any code outside of the player class, is going to interact with the state of objects of type player. So we have getters, which are going to have the syntax get and then the variable name. It's in camel case, so even though max HP starts with a lowercase m, this is camel case, so the second word gets capitalized, so it is capital M. So not directly the variable name, but get and then the variable name, no parameters, and then just return that variable. I can do this.maxHP because I'm inside the class right now. And then from outside the class, people will call this public method. They're allowed to call it because it's public. And then this will return the HP, the max HP of this player. So they can't access the variable directly, but they can go through this getter to be able to read its value. And they can use the corresponding setter to change the value of that instance variable. So the setter, the syntax is set, and then variable name, upper camel case again, takes the new value of that variable and then sets it. This.maxHP equals max HP, same thing we did in the constructor. And return void, we don't have to report anything back to the caller. So we're going to return void, which is our first useful method that returns void, aside from main methods, I suppose. Our first useful method that returns void. This method is called for its side effect. And the first method we saw like this, the side effect was printing to the screen, which isn't super interesting. But here's where that concept actually becomes interesting, valuable, useful, very important. Is the side effect here is going over to the heap and making a change to a variable in memory, making a change to an instance variable. That change will persist even when the stack frame ends. All of our changes to our local variables get destroyed, and with normal methods that behave like functions, those methods need to return something if they're going to affect the program. But now we can go over to the heap and make a change. That change will persist, and that's what we call a side effect of calling this method. There is a change, even though it doesn't return anything, it did change the state of the program by changing the state of one of the objects of that program. So we have a return void method that does actually do some important stuff. So this is how the outside world interacts with our variables. Instead of saying p1.maxHP equals, they'll say p1.setMaxHP to whatever value they want to set it to. And that's getters and setters. We will always have private instance variables in Java in 116. And use getters and setters to access those variables. I say sometimes there are some exceptions to this rule. Sometimes you'll see the keyword protected. The summer, or during the fall and spring, we actually have a case where you'll see the keyword protected. In the summer, some things get cut, and we actually won't see the keyword protected at all. I suppose you could use it in your problem sets when we get to inheritance and polymorphism. If you want to use protected, that's fine, but um, it might not even come up all semester. I probably won't talk about it aside from this right here. I think there's one point in the slides where I'll mention it just a little bit. But for our purposes, all instance variables private. Okay, but why? So this is the Java thing. This is just what we do. But I do want to give some background explanation instead of just saying Java getters and setters. I want to give some background. When I learned getters and setters, they were just kind of thrown in my face and said, we use getters and setters in Java, and then moved on. But I want to try to give some background. Why would we ever use a getter and setter? And the one-word answer is control. We want control over our code. And specifically, we want to make our code more robust so people outside of our code, people using our class, can't break our code as easily. So say we don't use getters and setters, we just make our instance variables public and let everybody access our instance variables directly. And somebody says p1.hp equals 16 trillion. Yeah, they have direct access to the instance variable, they can do that. What if they say p1.maxhp equals -3? Well, they can do that too. And now the player's just permanently dead. Those are things that we don't want them to be able to do. And somebody else on your team, because you're always going to be working on a team out there in the world, somebody else on your team is going to be creating objects of type player and messing with the whoever's writing the physics engine or the combat engine. Somebody writing the combat engine might have some complicated formula to calculate damage, and they might have some edge case in there that they haven't quite handled where the numbers just absolutely blow up. Maybe somebody deals -16 trillion damage and adds all that to the HP. We don't want them doing things like that. We don't do that on purpose. Like, it won't be sabotage. Potentially your end users could start hacking your code maybe, but usually it's something on accident that somebody else on your team does where they just miss an edge case or something. So if they have direct access to our HP variable and they set it to 16 trillion, there's nothing we can do. We're screwed. We just lost control over our state of our objects. They can just do that because they have direct access to the variable and we have no options. We cannot stop them. Like, they can just do that, and that's something we have to live with. So we don't want to have to just live with that. So we make our instance variables private and make people go through the setters. So now when we see somebody do that, we don't have to go knocking on their door and saying, hey, you got to fix your stuff because my code is crappy and you broke it. We don't have to do that. We're going to go to the setter and say, oh, somebody set HP higher than max HP. Well, let's just add a little check here because I'm already forcing everybody to go through getters and setters. Let me just update my setter, cap out HP so it can't go higher than max HP, and now we're done. 16 trillion just becomes max HP, 10 in our examples earlier, and problem is solved on our end. We don't have to change anything. We don't have to go, well, we do have to change something, but we don't have to go track down everybody else and make our mistake everybody else's problem. We don't have to do that. We just fix our setter, update our setter, problem solved. Same thing with getters. Sometimes we want to do formatting. I mentioned earlier with HP, we might want to display health bars. So maybe instead of get HP, just returning the raw HP, I might want to change this. We'd have meetings and talk to the whole team and everything, but we might want to change get HP to return a percentage of the max HP instead of just the raw HP. Well, if everybody's already calling my getter, I just update my getter, do a little math, do some division, make sure I avoid integer division, and then return that percentage instead of the raw HP, and now I'm done. I already forced everybody to go through my getter because I made my instance variables private. Nobody's accessing HP directly. I can update get HP to return whatever format I want them that they want to consume. I just update the getter and problem solved. If people are accessing my internal state directly, I don't have that option. I cannot control what they do because they're already accessing my internal state, which I have no control. It's just an int variable. I can't do anything with that. So this is why we set up our getters and setters even when we're not using them. I'm not doing anything with get max HP and set max HP or get HP or get name or set name. I'm not doing anything with any of these right now. But as long as I set up the getters and setters, even if I'm not using them at the time, I keep my options open for the future. So now if I want to do some formatting, I want set max HP to enforce that max HP has to be greater than 0. I can add that check. I can add that after the fact without having to have infinite foresight when I set up my class. Because this class is going to be used, in this example, in the full game, this class would be used all throughout the code base. There could be a dozen other developers all using this class in 100 different files. I'm not going through all that code and changing everything and telling everybody else to change it after the fact because I wanted to enforce this max HP can't be has to be greater than 0. I don't want to do that. I'm going to set up private variables, getters and setters, and then I can just add it after the fact. Everybody's already going through my setter. I add my check there. One change, done, easy. So that's why we set up the getters and setters. Even if they're not doing anything, it keeps our options open for the future. And if you're coding in Java, if you get hired for an internship or job and you're having public instance variables in Java, you might not have that position for very long. At the very least, you're going to get a sit down and you'll have nobody's going to get fired over something like that. I shouldn't say it like that. But it's very hard to get fired once you get a job if you're able to get in the door. You're there. Nobody wants to fire you after being hired. But if it's an internship, you might not get the full-time offer at the end, maybe. But at the very least, you're going to get a sit-down, like, public instance variables in Java. Let me talk to you about control and why we do this. And you'll get this speech again. So in Java, do this. Why we don't do this in other languages is because a lot of languages, especially newer languages, have mechanisms built in to be able to add getters and setters after the fact. So in Python, you can't make private instance variables. It's not even, access modifiers are not a part of the language. So everybody can just set and get your variables directly, your instance variables directly. But you can add a special method after the fact that makes p1.hp equals that syntax that they use actually behind the scenes call a getter method that you can add, and you can always change your mind after the fact. You can add that method after you've already created the instance variable, after people are already accessing the instance variable directly. You add getters and setters after the fact, and now the same syntax that looks like direct variable access is going to, oh, I'm covering up, it's just set name behind me. I got to pay attention to what's behind my face. It's get name and set name. And then that same syntax will call your getters and setters that you've added after you already set up the class and after there's 100 classes that all consume your code. You can still add those after the fact. Scala does the same thing. You can add getters and setters after the fact. Java doesn't have that mechanic, so we're stuck with getters and setters in Java. Okay, that's my detour on that. Let's keep moseying on. But that's why getters and setters. So if you're complaining about getters and setters, remember that speech. This is why we use getters and setters in Java. And then sometimes it can be helpful to call your getters and setters from your constructor, especially if you have sanitation like this with set HP, you have some check. You don't want to have to duplicate this code in your constructor. So if you call the setter, it can just save you some code, or you can still just set directly in your constructor. Either way is fine, but if you have more complicated setters, it's usually helpful to not duplicate that code and just call your setter from your constructor. Perfectly valid thing that we can do. And the one thing left that I purposely don't mention is that none of this is static. The keyword static does not appear anywhere. When I was going through every keyword in the constructor, for example, I omitted the conversation about static missing. I said everything's public static last week. That's not true this week. We're almost never going to see the keyword static anymore. It comes up a few times and does come up in the problem sets a few times. It'll say, make sure this one's static. This method has to be static, even though we haven't done static in a while. But most things for the rest of the class will not be static. The big difference between static and non-static is that static methods belong to the class itself. So any static methods in here would belong to the player class. Non-static methods belong to objects of that type. So anything non-static, which I'll just start calling methods from this point on. If it's a static method, I'll explicitly say a static method. But if I just say method, you should assume I mean non-static method. So all these methods belong to objects of type player. And they're called through objects of type player, not through the player class itself. We're not really going to mess with the classes very much moving forward. We're going to use classes to create objects and then mess with those objects. So we don't say player.getMaxHP, we say p1.getMaxHP. And we saw this in ArrayList and HashMap and list and dictionary in Python. We saw this all the time. I didn't highlight it too much because I was saving the conversation for now. If you have myArray of type ArrayList of integer, it's myArray.size, myArray.get, myArray.set. It's not ArrayList.set. It's myArray. I'm calling it through a specific array list object, and then I want to say I want to set the value, or I want to set the value. We used add in lectures. Set is if you want to set it at a specific index. I want to add this value to this specific array list, not to the array list class in general. That doesn't quite make sense. But this specific object, I want to get the HP of this player, player 1. I want to set the name of player 2. These are very specific objects that these methods deal with. And whenever we have a non-static method, that's when we have access to the keyword this, which is the object that called the method. So we have the context of that object, and we can access and modify its instance variables. And what we've done here is when we create a new class, what we actually do is define a brand new type. Like ArrayList and HashMap are both types in Java, and capital I integer, capital D double, capital B Boolean. These are all string. These are all types in Java that are defined by classes. And when we write a class, what we're doing is defining a brand new type in Java. So now that we've defined our player type with its state and all of its behavior, we can use this type anywhere where we could use any other type. So we can use player anywhere where we could use string, which is as the types of variables, including variables that are parameters of methods, as the return type for methods, and as type parameters in data structures. So I can have an array list of player objects now. I can have a method that returns a player, a method that takes a player. I can have a local variable named player. I can do all that stuff now because I just defined the player type and defined what the player type's state and behavior will be. So when I create a player object, I know this is its state and behavior, and I can tell Java, hey, I want a variable of type player, which will store a reference to a player object on the heap, and do whatever I could with any other type with my player objects. And they are going to be player objects, so they're going to be on the heap. So I want to make this crystal clear what goes on the heap and what goes on the stack. In 115, most everything went on the stack, and then our data structures went on the heap. Same thing in 116 so far. Everything went on the stack. Everything was stored by value directly, except our data structures, our array list and hash map. So let's make it very clear what is stored in a variable directly as a value. I say on the stack because that's usually where it shows up, but it's what's stored in the variable as a value and what's stored in a variable as a reference to an object on the heap. So in Java, in 116 at least, there's a few others, but in Java, it's all of our primitive values, our primitive types are going to be stored directly by value. That's double with a lowercase d, int with a lowercase I, boolean with a lowercase b, char with a lowercase c, but we didn't end up using this I don't think we use this in any of our examples or problem sets at the moment. But char is a single character of a string. If you want just one character, you can use the char. So if you want to iterate over the characters of a string, you would iterate over them as chars, as characters with the lowercase c char. Or you have uppercase C character spelled out is the object type for that. And then string we pretend is stored in a as a value in our variables, even though it's not. In reality, strings are objects on the heap. We pretend they're values, and same with our class equivalents for our primitive types. Those we're going to pretend are stored as values as well, even though those are also objects on the heap, which also kind of gets complicated. With modern compilers, a lot of compilers will convert these types into primitives after it's compiled for optimization purposes, so then they are actually stored as values. We're not getting into all that in 116. And our traces, all of these values, we're going to put on the, as all of these types, we're going to store their values directly in the variables. So in a variable type int is going to store its numeric value directly in that variable. And there are other primitive types. Primitive types are any type that starts with a lowercase letter. There are other primitive types. These are the ones we're going to see minus char. Double int mostly, and then sometimes boolean are the ones we're going to see in 116. We don't need to introduce, like there are different sizes of whole number values and different sizes of floating point values. Like there's float is a, let's not dive into it, but there are a whole bunch of different ones of these. There are also unsigned versions. We don't need to get into it all. These values are going to be stored in their variables directly by value. In 116, this list is exhaustive. Everything else is going to be a reference to an object on the heap. Everything else. So we already saw array list and hash map, but also any single object that's created from a class that you wrote or that I wrote or that anyone wrote is in Java is going to be on the heap, and our variable will store a reference to that object. Everything else. We're going to start seeing memory diagrams that are almost exclusively references all the way down. It's just going to be references all over the place. We're going to start seeing a lot of memory diagrams like that. So get used to references. You gotten somewhat familiar with it from 115 with lists and dictionaries, but we're gonna crank that up to 11. It's gonna be lots and lots of references. If you're not comfortable with references to objects on the heap, get good at it quick, get practice, go into the tracing tool, start practicing your traces, and that's actually where we're headed right now, is a trace to make this a bit more clear. But every object that you write is going to go on the heap, and we're going to do that a lot throughout this course. We will see lots and lots and lots of these. So that's your cheat sheet. If it's a primitive or a string or one of your object types for primitives, so if you're iterating over an array list of integers, for example, we're not going to treat that differently. We're just going to treat those as ints on our memory diagrams. All these are stored by value. Everything else is an object on a heap, and the variable stores a reference to that object. Everything. Absolutely everything. So let's do this with the memory diagram. As usual, I'm keeping the one in my slides that I made before I started doing these in the tracing tool. But we, today, are going to do it in the tracing tool. So let me grab the code. I'm tracing this simple player class. The player class, this is what we did in lecture, which I think is just a little more, we have attack power, so just a little different than what we saw in lecture. But I don't actually do anything with attack power, and it's hard-coded. It's hard-coded to 4. So this is the code that we just looked through in the slides. I'm going to use this class for the trace in the tracing tool, and cut down any of the code that's not relevant to the trace This is strictly just so it's easier to fit on one screen in lecture. And when I used to do these in the slides, it was so I could fit the entire trace on a single slide. So there's no other reason. I'm just trimming things down for logistical reasons. I'm in Python, switch to Java. Just weird because I had that other trace up. It's kind of weird that that was still Python. I'm going to paste this. I'm going to try to cut this down. I'm going to get rid of my package declaration for one. Get rid of a few empty lines here. Let's see if we can get this whole thing. Yeah, it looks like we can. Get this whole thing on the screen with the trimmed down version. And I'm printing out one thing, I believe. So let's try to leave enough room for one thing to be printed. Yeah, we're doing it. There we go. Get that whole button on screen. There we go. All right. Now let's start tracing this thing. This is usually the end of one lecture, so this would be spilling over into Wednesday in a regular week. But we got this. We'll get caught up by the end of this 2.5 hours. Okay. So every trace starts with the main method. No exception here. And very quickly we get into new content. So we have this simple player. I'm going to grab this in my clipboard because I got to type it a few times. And we have our very first constructor call. That's brand new territory. We're going to see, I want to say hundreds, probably not hundreds though. In lecture, at least dozens of constructor calls. Here's our very first one. Exciting time indeed. So we have the variable P1, which is going to get whatever is returned by new and then this constructor call. This is a method call. It behaves mostly like any other method call you've ever seen in your life, but there are a few differences. Actually, there's quite a few differences here. But it starts off just like any other method call. I'm going to create a stack frame. The name is the name of the method, which is simple player, which matches the name of the class. And the first difference comes right away. We're going to have the keyword this. We will put this in our traces. I don't know what the value is yet, but I got in the habit of putting the keyword this. I always put the keyword this right away. In fact, the keyword this is in every single stack frame for any method that's not static. So I got in the habit of whenever I'm calling a non-static method, which I'll just refer to as a method, I'll create the stack frame and just habitually create the keyword this in the stack. We do treat this as though it is a variable on the stack inside that stack frame. So I don't know what's going there yet. We'll circle back to that. But I also see the keyword new here. So the keyword new, actually let's get what else we know. We don't know what this is yet, but I'm always going to put that as the first thing. But we do know our parameters match to our arguments. So simple player, the constructor takes name and max HP. Name and max HP. This is old stuff. This is the stuff we know just because this is a method call. We have the parameters assigned to the arguments. Blanking on the word arguments. So we know that much. Okay, let's get into the literal new stuff with the keyword new. So the keyword new, we saw from ArrayList and HashMap that the keyword new is your cheat sheet. You should just be not even thinking about it like, I see the keyword new, I will click this button. That much we know from ArrayList and HashMap. And then the type of the object is going to go right here. I'm going to specify this is an object of type simple player. We always want to annotate what the type is for our objects. In this case, it's an object of type simple player. That's what we know from ArrayList and HashMap. Now we're getting into some new territory. We're going to map the constructor. Since we are tracing the constructor, we're going to map that by using this dropdown and choosing the constructor. This isn't strictly something that like happens in the computer. This is one thing we add to the memory diagrams to get the trace is looking looking better visually. What it does when you map the constructor is color code everything. So now I have light blue constructor matching to a light blue object. And every time I use this reference, it's going to be color coded. Oh, I forgot my return arrow. It's going to be color coded for that color. If you don't map the constructor, you don't get all the color coding, and your memory diagrams are just a bit more messy. I would consider that a minor mistake. I wouldn't fail anyone on a trace because of that, but it does make your trace much more clear. And then when we create an object on the heap, that object will get copies of all of the instance variables of that class. So I see I have new simple player. I'm creating an object of type simple player. I'm going to look at the simple player class, and then I'm going to look at all of the variables that are outside of all of the methods. If a variable is outside of all the methods, that is going to become an instance variable. Actually, I don't have any variables declared. I guess technically these ones. I have a few variables declared technically inside the class, but it's inside a method, so it's a local variable to the main method here. But any variables that are outside all the methods, those are my instance variables, and when I create an object, it gets copies of all of these instance variables. So we get max HP, HP, and name, which didn't get initialized to any values. I don't know what their values are yet. Technically, if you want to get technical about it, Java does have default values for all of your types. I can't. I want to get rid of those scroll bars, but whatever. Why is it even got a scroll? That we don't have any values here. Technically, this is going to be 0, 0, and I always forget about strings. Either null or empty string, I forget. But we're going to initialize our values anyway. Oh, and I do want to change the code a little bit here. This dot and name. Name equals name. Just because it's tedious and repetitive going through 3 setter constructor calls, you'll get the idea after just doing one of them. We're going to do 3. We'll do a bunch throughout the whole semester anyway. And then the next question is what's assigned in the keyword this? This, in the case of a constructor, is a reference to the object of the reference to the object that's being created, in this case OX100. And since I mapped my constructor, you can see that I have nice color coding. I get this light blue box around OX100 to indicate that it belongs to this object. So this is always the type of the object. For data structures, like if I create a new array list, its type is array list. So that was consistent, array list or hash map right here. Now, instead of creating an object from the class public class array list, which we'll actually see in a little bit here, we're creating an object from public class simple player. So it is still the type. But yeah, with data structures, we glossed over the whole fact that we're using constructors and objects and classes and everything, and we just said, yeah, it's the name of the data structure. But it is actually consistent. So all the stuff you did in 115 with list and dictionary here, that was the same thing that we're doing here. We just didn't explore all the details at the time. And then we run the constructor. So when you create a constructor, don't forget your keyword this. You create a new object on the heap. It gets copies of all the instance variables for that class. You put the parameters on the stack like any other method call. And then after all that setup, map your constructor, put the type of the object. So quite a bit of setup, quite a bit of steps that do admittedly just have to be memorized. And then once you have all that set up, then it becomes a method call, a regular method call again. You go through the code line by line. So first line of the constructor, this.maxHP equals maxHP. So this, which stores a reference, and this is why it's very clear when you have this on the stack, where this is a reference to an object. You treat this just like it's a variable that stores a reference, just like we did with array list and hash map, and then the dot operator, so this resolves to OX100. The dot operator says, hey, reference, take me to your object. So we go dot, takes us to this object, and then at this object, we're looking for a variable named max HP, which is right here. And we're going to set its value equal to max HP. Max HP is a separate expression. Every time we resolve an expression, we're going to start in the stack frame. So even though on the left-hand side, we made it all the way to this object on the heap, on the right-hand side, we start over. This is a new expression. We're going to start over at the stack and just directly look for a variable named max HP, which results to 10. So max HP on the heap gets assigned the value max HP from the stack, which is 10. So we get 10 over here. And then we have our one setter call. We're going to have this dot set HP. This is our first non-static method call that's not a constructor, at least, too. We're going to have plenty of these. We're going to see a lot in the next trace by the end of today, too. But this is our first one. So we're going to have a new stack frame. We're doing this dot set HP. So we're calling set HP from this object at OX100. We're going to create a stack frame for that method call. It's called set HP is the name of the method. And then it's a non-static method call. So we have the keyword this, which stores a reference to the calling object. Since we were at this object OX100 when we called set HP, then that is the calling object, and this is the reference OX100. Come on. So we have OX100 in this. So every method call that's not static is going to have the keyword this, and it's going to have a reference to the object being called. So then we're ready to call the method. Well, we have our parameter here, max HP. And I'll often do this when I'm doing traces. I know what the argument is right now. The argument is max HP from the constructor stack frame. So max HP is 10. This is 10. I'll usually resolve my arguments first because I don't know what I haven't looked at the method yet. I don't know what the parameter name is, but I know what the argument is. So I'll often do the arguments first. But now I'm looking for set HP, which was called from a simple player object. So I'm looking in the simple player class for a method named set HP, which I find right here. And I see the parameter is named HP, so I can fill that in. And then I have a conditional if HP, which is 10, is less than or equal to this dot max HP, which is 10. So this is true. Then I'm going to execute this code. This dot HP, this dot HP equals HP, a new expression, so I start over in the stack frame, HP, which is 10. So HP gets the value 10. End of that block. There were no variables declared inside the code block, so I don't have to add my dashed box. If there was a variable declared in this code block, I would have to have my code block there. We skip over the else, end of the method. Method is done. Doesn't return anything because it's void. But calling that method did effectively initialize this HP on the heap, and that change does persist after the method call ends. So even though this method returned void, it did have an impact on our program. So this method call just ended. We're back in the constructor, and this dot name equals name. This dot name equals name. Dark Cecil. We pretend strings are stored by value, even though they're references to objects. We're glossing over that in 116. And the stack frame ends. And when new constructor call resolves, it's going to resolve to a reference to the object that was created, in this case, OX100. If there are any questions on any of that, I would like to know. We're about to go through it again, but I'll go through the second constructor much, much quicker now that we've seen it once. But if there are any questions, especially as I'm going through this next one, Please, please, please let me know, because we're about to do it. So we have P2. We don't know what value it gets yet. It's going to get whatever this simple player returns. I have the keyword this, create a new object, map the constructor. I get copies of all of the instance variables of the simple player class. Max HP, HP, and name. I got OX200 as my reference, so that's my keyword this is OX200. Then I have my two parameters name. Max HP is going to get Kane and 14. Then I'm ready to execute the code of the constructor. This dot max HP equals max HP. Kane starts at 14. And then we have our method call, this dot set HP. It's called from this object here, OX200. So set HP, and this is, the memory diagrams are already getting large enough that I have to do some scrolling here. Set HP is going to get the keyword this, which is OX200, a reference to the object that called the method, and HP of 14. We resolve max HP from this stack frame. Max HP is 14. Set HP. HP 14 less than or equal to 14 is true, so this dot HP equals HP. This dot HP equals HP 14. Method call returns or returns void. No return arrows, nothing to do there. And then finally this dot name equals name Kane. Stack frame returns a reference to the object that was just created, OX200. Same thing we just saw, except I went through it a lot quicker. That's about how quick it should go when you're actually doing your traces. It should be automatic to do all those steps. You should be able to just breeze right through them. The first one takes a long time because I got a lot of new stuff to explain. And the third line, we got another simple player, P3. P3. And the arrows do sometimes cover things up. It's a little grievance, but not something I'm going to stress so much. Low priority. But P3 here equals P1. And since we do not see the keyword new, that's your cheat sheet to know that you're not clicking this button. You're not creating a new object on the heap. P3 equals P1. This is just like if you say int x equals 7, int y equals x. You're taking the value of P1. P1 resolves to OX100, and you're assigning P3 that value. So we don't really do anything here. We just assign the value. Done. That's this whole line. We don't have a constructor call. We don't create a new object on the heap. We don't do nothing. P3 gets the value of P1. The value of P1 is a reference. P3 gets a copy of that reference, not a copy of the object referred to by that reference, which is a 115 thing, but always good to have a reminder of it. And this, you can pretty well guarantee you'll see something similar to this on your OOP traces. And if you have this code, if this is a tracing quiz, this exact code, and I look at your trace and I see 3 objects on the heap, that's an instant fail. I know you don't understand references, object creation, constructors. I know you don't understand that if you have 3 objects on the heap. It's guaranteed you did not complete the OOP tracing learning objective if you have 3 objects on the heap. Easy instant fail, see you on the final. Don't make that mistake. If you see the keyword new, you're creating an object on the heap. If you don't see the keyword new, you're not creating an object on the heap. It really is that simple, at least for our traces here. There's at least one exception that I can think of off the top of my head. To that, you're not going to see that exception in 116 this summer. If you see the keyword new, you're creating an object. If you don't see the keyword new, you're not creating an object. And that's your kind of double check. You're done with the trace. You can look through and see how many times while tracing the code did I hit the keyword new, And do I have that many objects on the heap? If those numbers are different, go through your trace again. Find out where you went wrong, because you're not passing that trace. Make sure you at least have the right number of objects. There are a lot of little mistakes, like if you don't cross out your stack frames, or your math is off, or you have like 15 here because you thought it said 15 instead of 14. Like a lot of those things I don't care about. That doesn't have anything to do with your understanding of the learning objective, of the tracing and all that. But if you don't have the right number of objects on the heap, now I know you didn't understand the OOP learning objective, because I'm assessing OOP on those traces. I'm not assessing did you remember to click the button to cross out your stack frames. It's not a learning objective of 116. Simple mathematics, that's not a learning objective of 116. OOP, object-oriented programming, is. So if you make a mistake there, that's where you fail a trace. So I just want to clarify that a bit now that we know a bit more of what those tracing quizzes are going to look like. It's going to be a lot of constructors and objects and eventually inheritance. And I think I explicitly omitted polymorphism in the syllabus. I'll double check before I make the midterm. But I'm pretty sure I did. But we'll have inheritance on there as well. Okay, but let's continue with this trace. P1.setName, P1.setName. So we're calling it from this object, OX100. So we have setName. This is OX100. That's the object calling the method. And then we have setName. Sometimes I do this the other way. Name parameter equals Paladin. And then setName is going to be this. Oh, I'm covering up my stack frame. Let me get right in between the name and value. This dot name. So we're reassigning this variable here, equals name, which is Paladin. And Cecil is being promoted to a Paladin. SetName returns. It returns void, so nothing to do there. And then we're going to have printline p3.getName. So we have a getName method call. We have the keyword this. I don't know what it's going to be yet. I haven't traced it through. But p3.getName. So from this object here, we're calling getName, OX100. So this is OX100. GetName is going to... forgot about this typo. This dot name. If you don't have this dot, this code does the same exact thing as this dot name in this case. But I do like to be explicit and always have this dot, even when it is optional. But sometimes it is optional. I don't want to have that conversation right now. But it is sometimes optional. If you always use this dot when you want to access an instance variable, you don't have to worry about when it is and isn't optional. It's optional when there's no naming conflicts, but when there's no local variable of the same name. So this dot name is Paladin. So this returns Paladin. So this resolves to Paladin, and then we're going to print Paladin to the screen. So when we called setName, we changed P1's name. If you're just reading the code, this might be easy to miss. We're changing P1's name to Paladin and then asking P3 for its name. But P3 sees this change because P1 and P3 are referring to the same object. They have references to the same object. It can be tricky to see, like I just said, when you're just looking at the code, it's easy to miss. You should all know this from 115, but it can be easy to miss when you're looking at the code. But when you're doing the trace, I don't even have to think about that at all. I don't have to think that P1 and P3 are referring to the same object. I'm just blindly going through the code, and when I did P3.getName, I had this being OX100 and just went over there, looked at the value. Oh, the value happens to be Paladin. I don't know how it became Paladin. It just became Paladin. I don't know. Just tracing through the code. That's what the computer's doing too. The computer doesn't think about this stuff. It just blindly goes through the code. So when you're doing your traces, it can help to not overthink things. I've seen a lot of students fail a lot of traces by overthinking things and kind of predicting what they think the code is supposed to do and then working backwards from that to fill in the trace. Don't do that. Just trace through the code. Just trace through the code. And you don't have to work as hard, and you'll pass more traces. And you'll understand more about what the computer's doing. It's a really big win if you just trace through the code line by line, kind of blindly. Okay, so that's that trace. And let's press on. If there are any questions, I'll keep looking in chat for questions. But since it's in this format, I don't really have to stop for questions. I'm just going to always look at chat. If you ever have a question, post it in chat, and then I'll find a good stopping point to be able to jump to your question. It's not like lecture where, a live lecture, where you kind of got to stop for questions, and I don't know. Just different format, so I'm going to keep on trucking, mostly because you can pause. I usually stop for questions in a live lecture, just so you have time to digest what the hell's going on. In a live stream, you can just pause the stream. Like, of course, once you pause the stream once, I guess you can't ask questions anymore. But if you ask a question about something that happened a while ago, I'd still answer it. It's a more flexible format. So let's continue our conversation about classes. And do I even give this disclaimer? This makes more sense when the structure is Monday, Wednesday, Friday throughout a whole week. Now we have a whole week's of content in one lecture. Maybe it still makes sense to say. But at the beginning of a lecture in the summer, what I like to do is get all of the content. It did seem the tracing with you, and it didn't seem that bad. Oh, sweet. Like to hear it. So the beginning of each lecture, the first like 50-ish minutes, which would be usually the Monday lecture, that's where I like to just dump an entire concept on you. So I said everything I need to say about objects, classes, constructors, the keyword this, encapsulation. I said everything. It's all out there. But it probably, if it's your first time seeing these concepts, probably didn't make a ton of sense. Probably made a little bit of sense, you know. And then the rest of the lecture, which would be, now we're getting into what would be Wednesday, and then we'll get into what would be Friday. The rest of the lecture is reinforcing what I talked to you, what I told you on the first portion of the lecture. So now we're going to go through the same concepts we just saw, but from a different angle. And specifically, I want to show you the same concepts from the array list class. So we do say new array list. We know array list is a class, and we're creating objects of type array list. And we have a constructor, an array list constructor. We know all that stuff now. So let's crack open the array list class and talk about all the concepts we just talked about with the player class, but in relation to the array list class. And what would be the Friday lecture is one big memory diagram that takes everything we've seen so far and puts it in one massive memory diagram that we'll muck around with for a while. My dog's over there crying. I don't know what he's crying about. All right, so let's do it. So we saw a new array list and then a constructor call. We also have the type parameter. That's something we'll ignore today and then talk about on Thursday. We will dive into that and know all about type parameters on Thursday. But we'll gloss over that for now. But we have new array list and a constructor call, and this constructor takes no parameters. What that does is gives us a reference to an array list on the heap, and then we can store our values in that array list on the heap, and then our variable just stores a reference to that object, that array list object on the heap. I always forget I do this in multiple slides. So, and if we want to access that, R1 is a reference, dot takes us to that object, and then we can call methods on that object. So add is a non-static method of the ArrayList class. We're calling it through an object as opposed to a static method that we call through the class. You do problem set 0 dot sum of digits to call those static methods. But here we have non-static methods. We're calling them through a specific object. I want to add this value to this ArrayList object. I need to know what object that is, and we do that by calling it through an object, and then the add method will use the keyword this to add it to that specific object on the heap. All right, I gotta see quick what my dog's. He had his toy stuck under a box. I need to free his toy for him. So we use the dot operator to access that object, and we can call methods, and the method will be called in the context of that object, which it accesses through the keyword this. So let's see how all that works, and I'm going to actually crack open the ArrayList class itself. If you want to do this yourself, you can go to our ArrayList, any ArrayList example. If you have the ArrayList class that you're using in your code, you can do Control-click or Command-click on Mac. Click on it, and it'll actually take you to the ArrayList code. You can see tons of code here, lots of documentation for the ArrayList class. If you want to know exactly how the ArrayList class is defined, you can go through all this code and see everything. It uses a lot of advanced syntax that we haven't talked about yet. But you can see that it is public class ArrayList. It is a class. It has to follow the same rules that we follow when we create classes. There's no magic here to an ArrayList. An ArrayList follows all the same rules we follow. We could create a class and call it ArrayList2 and create the same exact thing that ArrayList does to the T. It do absolutely everything an ArrayList does. Nothing special about it. It's just a class written in Java that enough developers have use for that they decided to just ship with Java itself. So we have it in this Java standard library. But it is just code written in Java that we could write ourselves. Same thing, has to follow all the same rules. So in the slides, I'm going to significantly trim down the ArrayList code. I'm not, oops, oh, that's fine. I'm not going to show every piece of code. I'm going to significantly trim down just so it, one, fits on a slide, and two, we're not getting overwhelmed with all the extra stuff. You can already see I trimmed quite a bit from the first line here. We saw extends and implements. That's inheritance stuff that we will talk about later in the class. Not today. We got enough to talk about today. We got enough new concepts I'm throwing at you today. So we are in the Java util package. That's what we expect. And the class is ArrayList. This is what we expect because we said import java.util.ArrayList. So we know the package was java.util and the class name was ArrayList because that's how we import it. So we can actually go to that code and see how that's defined. When we use it, just mention that, that's what we import, so we knew these two things already. And we also know that there's a constructor that takes no parameters because we called it. We called that code. We used that code. It has to exist in that class. There's no other choice. Like, it has to exist. It has to exist in that class. And in fact, it does. We have a public constructor for the ArrayList class that takes no parameters. I'm omitting the code for now of that class, but we know that constructor has to exist. So this much we know exists just from how we used ArrayList. We also know it has a few public methods, add, get, and size are the three that we've seen so far. We know those three public methods exist as well. We also know there's a second constructor we saw at I think it was the very first slide today, that we saw earlier today, that there's another constructor that takes a list of values and populates an array list with those values. And this takes what's called a collection. We have some extra syntax here, something that extends E and E, the type parameter we're not talking about. So there's some logistics here, but this takes something, some collection, some list, some data structure, there we go. Some data structure of values And then I removed the code for the slides, but you can kind of predict what it does. It'll iterate over C, it'll iterate over all its values, and then add all those values into the new array list that we're creating. That code I'm not going to show you. You know, feel free to look at it if you're interested, but it's not relevant to the concepts of the day. So we know those two things exist, and this is allowed. Oh, that was on this slide. This is allowed. We have two constructors. We can absolutely do this. We can have as many constructors as we want, as long as they have different parameter lists. This is something called method overloading, or in this case, constructor overloading. If you have multiple methods with the same name, as long as they have different parameter lists, that's perfectly fine. And then when you say new array list, if you give it a parameter that happens to be a collection, then it's going to call this constructor. If you give it no arguments at all, then it's going to call this constructor. So Java will look at the arguments you provide and then call the method with a parameter list that matches those arguments. So we can absolutely do this and have many, many methods with the same names. Something you can't do in Python, but I guess that's not relevant because you never did OOP in Python. You never created a class in Python in 1.15. But if you do, you can't overload your methods. Suppose you could have, it doesn't matter. Suppose you could have functions and do the same thing, but you can't do that in Python. No overloading in Python. But Python gives you keyword arguments and well, it doesn't matter. Not relevant to today's concept. But there are ways to get the same behavior in Python, just different syntax. And a class is a container for state and behavior. We've seen some of the behavior of the array list class. We saw add. This dog has problems. We've seen add, size, and get. We know some of the behavior, but we don't know any of the state. And that's on purpose because we like to hide the state. The state's private. We can't access these variables anyway. They're private. There's no need to ever know about these variables unless you're studying how the ArrayList class works in an educational setting. Of course, we're going to talk about these things. Or if you're working on the Java standard library itself and trying to make changes and stuff, then yeah. Other than that, you don't need to know about these. If you're using an array list, you never ever have to care about these things. Because and that's why they're private. They're private. That's a way of us saying, of the developer saying, you don't need to know about this stuff. But we're in an educational setting, so let's talk about it. There are two instance variables in the ArrayList class. One, element data, which stores all of the actual values that are in the ArrayList. And we can see that this is a plain array. These do exist in Java. This is one of the only times we'll see it in this course. But plain arrays do exist in Java. We have this array of objects that actually stores the underlying data that's being stored. And as a separate variable, they're storing the size as an int. There are lots of reasons for that. I don't think we'll have time in the summer to go over it. In the regular semesters, we do talk about the difference between arrays and array lists in Java. If I find some time, I'll briefly go over it, but I won't be able to give it a whole lecture like we do in the regular semesters. One of the things, unfortunately, has to get cut for time for the summer. But it does track its size independently for very important reasons that I don't have time to really dive into. And then when we ask for the size, when we call the size method on an array list, this is effectively just a getter method for the size variable. So you can see the developers of Java do follow the convention, private instance variable, and then have a getter method for that size. The number of times throughout all the code bases in the world where this size method is called, if they want to make a change to it, they just change it here. If we were all accessing the size instance variable directly as a public variable, there's no choice. If they want to change the way we access the size of an array list, it's not going to happen because they expose their instance variable. So they're making this private, giving us a getter, and then if they ever do want to change this, hopefully they don't because they'll probably break lots and lots of codes, probably at least 1 million instances of this method being called out there in the world. they'd break so much code if they make any change to this. But anyway, they have that option because they're going through a getter. So we have state and behavior. The state, 2 instance variables, and then behavior, all the methods. And the default, so when we call the parameter list constructor, the actual code is just this one line of code. It's going to initialize element data to a static object that is an empty array. This is the syntax to create an empty array. So they have one copy of an empty array. I don't want to get too lost in the details here, but I'll briefly talk about it. So this variable is static, meaning it belongs to the ArrayList class, which means there's only one copy of the empty array. Final means that its value cannot change. So if you try to reassign this variable, Java won't let you. It'll say you declared this as final. Whatever you assign it to initially, that is its value forever. So this is their way of having only one copy of the empty array across all array lists. They all refer to the same empty array. So they're being a little space efficient. So if you have 10 empty array lists in your code, you only have one empty array object on the heap instead of 10 copies of empty arrays, which is just wasteful. So it's just a small optimization that they do in the code. Again, this code is used millions of times out there. Any even tiny optimization is going to improve a lot of code bases. A lot of code bases, just a small amount, but a lot of code bases. So they're going to do everything that they can do to optimize this code. They've been working on it over decades. Teams of developers for decades. They're finding every little optimization, and this is one of them. But we can find use for static variables, is the point that I want to talk about right here. That we can have static variables. And also that the constructor, the whole point of a constructor is to initialize the variables. They are taking advantage of another optimization here. When you declare a variable in Java, I briefly mentioned that it gets a default value. The default value for int is 0. So they're taking advantage of that and never actually initializing size and just leaning on the default behavior of Java to get size initialized to 0 without having to waste an extra line of code. Again, every drop of efficiency here is useful in the standard library. And then the other methods that we're used to. So get is going to access that variable at an index, the value at an index. And it does use the array notation since this is a plain array that's working under the hood to make an array list work. Oh, I'm a little... You know what? Oh no. Let me move myself just for, at least for this slide. I want to make sure y'all can see all this code. So the get method is going to access that variable and then do some extra stuff. We don't have to worry about the type parameter stuff at this point, but it's going to return the value at that index. And the add method is going to do a bunch of stuff. I'm not just going to leave it at that, but that's my lead-in. It's going to do a bunch of stuff. And there are two add methods. This is overloaded. They have different parameter lists, so that's fine. So the add method is, I feel like I have these slides out of order. I want to jump to this one. The add method that we call is the public one. So when we access the add method, when we use the add method to add an element to the next available index, all we want to do is tell it, hey, this is what I want to add. Done. I don't want to have to tell it anything else. But to get the job done, to actually do the work of the add method, they want more parameters. They want to know the current size of the number of elements in the array list and the current element data that we're working with. And I'm sure there's a good reason for this, but I don't know why they don't just access the instance variable element data, why they pass it, actually for size too, for that matter. I'm sure there's a good reason, but anyway, this is the way they have it set up. And then they're going to check if they have more room in the array, and if they don't, they're going to call another helper method called grow, and then finally add the value and increment the size, a bunch of stuff. The details aren't too important right here. In CSE 250, you'll go through all the details of how this works. For 116, what I want to highlight is that we don't have to care how any of this works. We're going to get a public method called add that takes a value that we want to add. That's all we need to care about if we're going to use the ArrayList class. So that's what they make public. And then this helper method that takes 3 parameters and grows the underlying array and all this stuff, all those details, nobody using an array list using this class really needs to know how any of that works. So they're going to make that private. So any of the details are going to be hidden from us. We have never, until this day, until today, you've never cared, and hell, you still might not care, but you've never cared that there's 2 instance variables in the ArrayList class, that there's an underlying array, and that the size is tracked separately instead of just asking element data for its size, which you can do. You can ask it for its length, but we can't really do that the way things are built. And then there's this helper method, the add method, and also a grow method, which is also private, that there's all these details. You don't have to care. And this is the concept of encapsulation. Encapsulation is where we're hiding the details. The developers of the ArrayList class said, nobody needs to care about this stuff. Nobody needs to care. If you're just using an ArrayList, you don't need to care how we actually implemented the functionality of an ArrayList. So let's just hide that. Let's make it all private so you don't have to care about it. You can't call these methods. You can't access these variables. And that's fine because you don't have to. Nobody needs to care. Nobody needs to access this stuff. But the stuff that you do need to access, we're going to make all that public. And we're going to make all of the behavior that you want to actually use public. And these are the methods that we've actually used in the code for an ArrayList. We used the 2 constructors. We asked it for its size. We added elements to it. We got elements by index. All that's public. This is called the public interface for the class. And this is how anyone outside of the class interacts with this code, is through the public API or public interface. That's how we interact with it. And we don't need to care about any of the private stuff. So encapsulate all the private stuff, all the details, and then expose publicly the API, how you're going to actually interact with the code. And we could expose public state, but not in Java. We're not going to expose public state. But in some languages, you would expose some state as well if it's important to the outside world. Not in Java, though. We don't do that in Java for the reasons discussed earlier. For control. And the keyword this shows up in all these non-static methods. This is how our non-static methods are going to access the current state of the object. So the size method, this size method here isn't being called on the ArrayList class. We're not just saying ArrayList size me. No. What we're doing is saying I have a specific ArrayList. I have this ArrayList of strings in my code. I have an object, a reference to it. I have a reference to this object on the heap. Tell me the size of this ArrayList. This ArrayList on the heap in my code, I want to know its size. Tell me its size. So you say my list.size, that's going to call size in the context of that specific ArrayList object, and the method is going to use the keyword this, which stores a reference to the object that called the method, and ask it for its size instance variable. Because if I have 3 ArrayLists in my code, I want the size of a specific ArrayList. And I'm going to call the method through that ArrayList. That method gets a reference to that ArrayList through the keyword this, and then can ask this for its size. That's how we're getting the behavior specific to an object, not to the class in general. This class is used to create many ArrayList objects. We're interested in those objects. That's why none of these methods are static. We have one static variable, which is shared across every ArrayList for the reasons we discussed earlier. So we're only creating one empty array for optimization reasons. Otherwise, everything is non-static. I want to know about a specific ArrayList. I want to add a value to a specific ArrayList. I want to get the value at an index for a specific ArrayList. I want to ask the size of a specific ArrayList. I don't want to ask the ArrayList class. I'm asking ArrayList objects. That's why these methods are non-static. and we get the behavior we want specific to that object using the keyword this. That's why the keyword this is crucially important, storing a reference to that object. I did mention earlier, sometimes it's optional. You don't have to have this dot in this instance. You can just say return size. You might have seen code like that before. You might have written code like that before if you coded in Java before. Sometimes it's kind of optional, but when it is optional, what Java is doing is pretending that you did type this dot. It's saying, you know what, I know what you meant. Let me just fix that for you and go over to the heap and access the instance variable anyway, even though you didn't say this dot. Otherwise, you got a compiler error. I'm not going to tell you it's a compiler error and tell you to fix it. I'm just going to go over to the heap because I'm pretty sure that's what you meant. So sometimes it is optional. I recommend always putting the keyword this for readability purposes, if nothing else. It makes it much more clear what your intentions are if you have this dot in your code. And static belongs to the class. So before, just kind of like what I just said, default capacity empty element data. In the earlier slides, right here, this is what it looks like in the actual code itself. It's just this. And Java says, I know what you mean. I know you mean this variable. Let me just use that variable for you. But what we are doing is calling it through the ArrayList class. So it's more verbose to say, and more descriptive to say ArrayList the class dot default capacity empty element data. Any static variable or method is called through the class itself, like problem set 0.average. It's called through the class itself. So this static variable can be accessed through ArrayList dot and then the variable name because it's static. We're accessing it through the class itself, not through an object of its type. Yeah, static referencing. And not through an object on the heap or anything, it's through the class itself. Okay, and again, I'll keep watching for questions, but there are questions on this. I'm going to keep on trekking, and then if there's a question, I'll always go back to a slide if I need to. But there's one other class that we've seen. Oh, did I even show any of this in lecture? I might not have. No, I don't think I did. I think those examples get kind of washed away. But there is the math class. In pretty much any language, you're going to have a math class with all the standard math stuff that you would want to use. Java is no exceptions. We have the math class, which has lots of methods available to us that we can call. The math class, and sometimes this is useful to do, the math class is actually a collection of static methods and even some public static variables, which is kind of wild. After I say we use private instance variables and getters and setters, we have a little bit different setup here, a little bit different situation where this is good to do. But math is a collection of static methods. So here I have the absolute value method, ABS. It takes a value and returns its absolute value. It takes an int and returns its absolute value. And this is a static method, a public static method. So when we want to call these methods, math is in Java Lang, so it's auto-imported. You don't have to import the math class. But in your code, you can do math.abs. You're calling the static method through the math class itself. You do not have to say new math, call the constructor, and then from your math object, call the methods, because these are static methods. So absolute value, sine, cosine, power, whatever math method you want to call that's in this math class, you call through the math class itself because they're all static. And if you want a complete list of all of the math stuff, all the math methods that you have, if I want math.pow to the 100, which is a crazy huge number, I can do control-click on the math class. And you can scroll through here and see, you can see how much I trimmed out the documentation for the slides and a bunch of stuff. But you can scroll through here and look at every single method you have available. I have sine, cosine, tangent, arcsine, arccosine, arctan, 2 radians, 2 degrees, e to a power, exponentiation, logarithms, log base 10, square root, I don't even know what that one is. Court, cube root. Oh, that makes sense. Cube root, blah, blah, blah. Lots of methods that you have available to you. So whenever you're doing some math, if you want to know everything that you can possibly do that's available to you, take a look at the math class and see everything that's in there. I just have one method here as an example of a static method. And this comment is actually in, I'm not going to jump back to IntelliJ here, but this comment is actually in the, you know what, I might as well, is actually in the math class. So we have the math constructor, and it actually says, don't let anyone instantiate this class. So what we have is a private constructor, meaning if you try to do new math, it actually isn't going to let you. This is a way to prevent anyone from ever creating an object of your class type. And the math class is a collection of static variables and methods, so there's no need to ever instantiate the math class. In fact, they're not even going to let you. They made the constructor private, so you can't even call it. You might ask, well, why not just not write a constructor at all? If you don't write any constructor, you do get what's called the default constructor for free, which is the same as this constructor, except it's public. So public takes no parameters and doesn't do anything. In your problem set 0, if you want to create an object of type problem set 0, you can do new problem set 0 and give it no arguments. You'll get a problem set 0 object. There's no non-static methods in problem set 0, so it won't be effective. It won't really do anything for you. But you can do it because you get the default constructor for free. So the math class, they say, nah, we don't want the default constructor, so we're explicitly overriding the default constructor with a private one, so you cannot instantiate the math class. Math class also has some constants. So I've called these variables a few times, but they are actually constants because we're using the keyword final, just like that variable, the static variable in the ArrayList class. This is public and static, so everybody can access this from anywhere in any way without creating any objects or anything. But it's final, so nobody can change the value. You can't do math.e equals 2.7. You're not allowed to override these values because they're final. They can't be reassigned. So when something's final, it's a constant. And constants, it's fine to make constants public since nobody can change them. And when you have constants in your code, it's convention to name them with all capital letters using snake case with these underscores if it's multiple words. And they have these degrees to radians, radians to degrees. For some reason, they made this private. I'll probably never know why they made these private. Those would be useful to have for everybody, but they made them private. But they use them in several methods. But, I mean, they could have just exposed these to us, but they didn't. But if you ever want to use pi or e or tau in your code, use math.pi. If you're working with circles and stuff, you need pi, use math.pi. Do not declare your own variable. Double pi equals 3.1415. Don't do that. Do math.pi. This is going to give you pi to as much precision as can fit in a double variable. So this, if they added one more digit, it wouldn't fit in a double anymore. They give you as much precision as you can possibly fit in a double. So this is the one you want to use, so you have the most precision and the most accuracy in your code. Same with e, same with tau. Use these constants if you need them. So static is still useful, like the math class demonstrates. And then toString. This is kind of a one-off topic. We'll talk about this concept more when we get to inheritance. But if we print our object to the screen, if I just say print line P1 of my object of type player, it's going to print something like this. These days they'll say topic2 underscore classes dot player at, and then some hex value like this, which is pretty much never what you want. I say pretty much, but I haven't really had a case where that's what I wanted. That's not what you want. But if you do just print your objects to the screen, you can print them to the screen, but it won't give you what you want. But we can write a special method called toString. If you write a method named toString that takes no parameters and returns a string, whatever string, and make sure it's public, whatever string this returns, whatever you return from this method, that's what will be printed to the screen when you print your object to the screen. So println knows to call toString on this method, and then whatever toString returns, that's what's printed to the screen. When we get to inheritance, we'll talk about the mechanics of why this is the case and how we get this behavior. But for now, just if you do want your objects printed a little more human-friendly and with more useful information, write a toString method with this signature, and that's the behavior you'll get. And since we defined, with our player class, we defined a new type. Just to emphasize this point, we define a new type. We can use that type as the type for our variables, types for our parameters. We don't have in this example, but we can have it as the return type of a method and as the type parameter of a data structure. So just a reminder that what we're doing here is creating new types when we create a new class, which is really relevant right now because we're going to go through the a big old memory diagram. We're shifting into the what would be Friday content now. We're going to look at this memory diagram right now. I'm not even going to bother downloading these slides because it very quickly just jumps into a memory diagram. I'm going to do it all in the memory diagram. But in the slides, there's two things that I want to highlight that are going to come up in the memory diagram. One is composition. This is a big fancy word that I really don't like. I'm not big on vocab, but this is one that I just at least want to mention what this is called because some people like to call this composition. When you have an instance variable in a class for its objects can be another class type. So you can have an object that has an instance variable that's a reference to another object. Now, I think that's just kind of intuitive. Like, we're creating a new type. Variables can be any type. Instance variables are no exception. Instance variables can be object types. But for some reason, they give this a big fancy word, composition. If you ever hear somebody say that word, they're just being a little too fancy, in my opinion, about what variables can do. Variables have types, and types can be objects, and instance variables are variables. Its type can be another object. So in this memory diagram, we're going to see that in action, though. I don't like the vocab, but the concept is critically important, is that we do have an instance variable that is a reference to another object on the heap. And absolutely we can do... Oh, I don't want to highlight anything. Absolutely we can do that. And the other concept is garbage collection. This won't come up in your traces, but it is something I just want to make sure you're aware of, that I get this concept out there. So we're going to create a character assigned to the hero variable, and then immediately reassign hero to a new character. This original character that was created can no longer be accessed by our code because we lost the reference to it. Whenever that's the case, that object will be garbage collected. Java will go through and erase it from the heap for us. And then we can no longer access that ever again. It doesn't exist anymore. So those are the two new concepts for this trace. So let's grab the code. I'm grabbing this from... So the code is spread across multiple classes now. We have a multi-file program. We have the party class, the character class, and I think the main method, the main method's in the party class in this example. So I guess it's only two files. But just to make it easier for me to grab for the trace, I put both classes in a single file. So this is the code that I'm going to trace. It's the same code, I believe exactly the same in this example as what I have in the two classes. It's like having them both in one file, so it's easy to grab. Inheritance, you'll see this a lot. I have multiple classes I'm going to put in one single file just so I can grab them for the traces. So that's why I'm grabbing the code from there. So let's go to our tracing tool. Let's blow this thing up. Boom. And let's paste our new code. This one I really don't think I can fit on the screen. I might try... making this smaller. If it gets too small, make sure you let me know. I think I can get away with this. Yeah, I should be able to get away with this. Would tracing a two-string method work the same way as tracing any other method? Yes. Or is there something different about it because it's special purpose? So you trace it just like any other method. The one thing you have to know about two-string, and actually I think I'll just avoid this on the traces this semester. The one thing you have to know about two-string is when you call the print line method on an object, the print line method is going to implicitly call the two-string method. So you do have to know that when you see print line and then some object, that you do have to trace through the two-string method. But I think I'll just avoid that. I'll make the two-string calls explicit. And then when the two-string method call is explicit, it is literally just like any other method call. Okay. And do I even print anything to the screen here? Nothing's even printed to the screen, so I'm going to gobble up all my I.O. Maybe I can just... No, I want to try it at this size because there will be a lot of traces later that where I'll need more space. Do it right here. And I'm going to have a lot of stuff in the stack and heap. I think I want it set up like this. Okay. Let's do this trace. We got 34 minutes to do this trace. We can do this. So every Java program has always started with the main method. We're going to start with the main method here, and we have a variable hero, which is being assigned whatever new character returns. So new character, we have our another constructor call. So I have my constructor, if I can spell, character, I have my return arrow, I have the keyword this, I don't know what value it gets yet. And since I see the keyword new, I know I'm creating a new object on the heap. It's of type character. Its constructor is the light blue character. And I'm looking at the character class for any instance variables. Now, we haven't even gone through this code yet. We haven't looked at what it does. You can mostly, I think, guess what it's going to do. We're creating this hero who's going to win a battle and gain 10 XP and mark as one battle won. And we're creating a party with two characters in it. They're going to win a battle, both gain 20 XP, and both get one battles won, increment this by 1, and also mark that the party collectively has won a battle. Like, that's the end goal of this. The hero should have 30 XP. The fighter should have 20 XP at the end of everything. And the hero won 2 battles. That's what we're doing. That's what the code's doing. And I don't think that's too complicated, even if you haven't programmed in Java a day of your life. What we want to focus on with this trace is exactly how all of the mechanics work, how everything works in memory, so we make sure we nail down every single little detail, because that's what you need to do in your traces. Be able to know not just what the code does, but how the code works. That's what we need to get to in 116. So it's not too impressive to know what this code does. You obviously have to know what the code does as well, but how it does that and why it does that. So you really understand how the programs work. So then when you're looking at even more complicated programs, you can still follow through them. When you're on the job and looking at a huge code base, you can still intuitively know what's going on and why it's doing that. Because sometimes you'll be looking at code without the context. Like if you understand the context of playing an RPG where you're winning fights and getting XP. But if you're looking at code where you don't understand the context, that's where you just straight up have to know how code works. So that's what we're focusing on here. So we create the character object. We have 2 instance variables. These instance variables are initialized right in line. So battles1 is 0. And exp points is 0. And the constructor keyword this gets OX100, a reference to the object being created. And the constructor doesn't take any parameters. I didn't give it any arguments, so we're good there. And the constructor actually doesn't do anything either. So it just returns right away, keeps the initialization of 0, and then returns OX100 to the stack, to that variable. I tried to keep these constructors simple because I got to go through it 3 times. So next we have the same thing. We're going to have a character. Let me grab character in my clipboard so I don't have to keep typing it. Character, this. I see the keyword new, so I'm going to create a new character. Its type is character. Its constructor is the dark blue one. We have battles 1, 0. Has not won a single battle yet. And experience points. So this is a case where we have a constructor, but the constructor doesn't have any work to do because we're having the initial state of every object being identical. Everybody starts with 0 battles 1 and 0 XP. We could have all their like strength stats and everything, but we're not making this example that complicated. So there's nothing for the constructor to initialize because every character starts in the same initial state. And then we're I didn't miss anything, right? Yep. Crossing this out and then updating hero. So this is being assigned to the hero variable, which gives it OX200. And at this point, this first character at OX100 is unreachable. There is no, after this line 28 executes, there's no possible anything. There's nothing I could possibly type here in my code to be able to access that object again. I don't have a reference to it. I know it's somewhere out there in the heap, but since I lost that reference, I have no way of getting to it. I have no way of finding it again. I have no idea where the operating system gave me that memory in the heap. The only way I knew how to access that memory was through that reference it gave me. But I took that reference and threw it away and replaced it with OX200. So I have no way of reaching this object. So what Java will do is delete this from memory. It's going to recognize that I can't access it anymore, and it's going to delete it for me and free up that memory, which is an extremely important and extremely useful feature that you're never going to notice until it's gone. So in Java, we'll just take garbage collection for, it's called garbage collection. We'll take garbage collection for granted this semester, and it's just going to do a lot of work behind the scenes that makes our life a lot easier, way, way easier. When you get to CSE116, you're going to code in the programming language C, which does not have garbage collection. And once garbage collection is gone, that's when you really understand what it's doing for you. It's really hard to explain what it's doing for you when it just makes your life so easy you don't have to think about it. But once it's gone, that's where you'll learn it. So aside from this little note right here, I'm not going to talk about garbage collection. Unless y'all ask, I'll be happy to talk about it. But it's not really relevant to 116 concepts. 220, despite not having garbage collection, in general, memory management. Garbage collection makes memory management easy. 220 is going to force you to manage your own memory where you do the job of the garbage collector. That's where you learn what garbage collection is when you have to do it. Oops. Okay, so now let's get fighter. But this object, that first object, OX100, doesn't exist anymore. Or rather, it's a candidate for garbage collection. We don't get to control when garbage collection executes. Our program might finish before garbage collection runs even once, or it might execute right after that line of code. Java does its own thing, has a mind of its own in that case when it comes to garbage collection. Okay, let's get our fighter, map the constructor. We have battles 1. Never won a battle. Experience points. Doesn't have any experience. This, we got OX300, and the tracing tool will just go OX100, 200, 300, 4, 5. It'll just go sequentially like that. The operating system will give us not random values, but random to us values, randomish values for those. But the tracing tool, just to keep things kind of clean and simple, it'll go increment by 100 each time. But these can be anywhere. When you run the debugger on your code, you'll see the values are actually just all over the place. They're going to be wildly different. Okay, we got our fighter, and then the hero is going to win a battle. So hero dot OX200 win battle. So we're calling win battle from this character right here. Let's get everything that we know so far. We know we're calling a method named win battle. We know we have the keyword this, which is OX200, a reference to the object calling the method. And we know that the argument is 10. We don't know what the parameter is just yet. Because we have one big thing we need to resolve right now is which method are we going to call? And this will be a topic right now through classes and objects. It'll be a topic for inheritance. It'll probably be the biggest topic for inheritance. And then again for polymorphism. I'm going to ask this question a lot. Which method is being called when we call a method? Because we have a win battle method here and a win battle method here. We have two methods named win battle. So we can try to resolve it with the parameter list, but both parameter lists just take an int, and we are providing an int. So we have two method signatures that match the method that we're calling. And hell, we're calling win battle from, like, this code is inside the party class. Maybe I should call this one. How do we resolve which one that we need to call? And the answer is always, throughout right now, inheritance and polymorphism, this will be the same answer all the whole time. So if you get this now, you got it. Is by the type of the object that called the method. So this dot, let's go to the object that's calling the method, which is always the reference of this. This is the object that called the method. It's of type character. So I'm going to look in the character class for a method named win battle that takes an int. I find it right here, and this is the method that's called. It depends on the type of the calling object, not where the code lives, not anything else, not even the type of the variable that won't become important until polymorphism, but not even the type of the variable of the object, of the calling variable. Calling variable is completely irrelevant in any conversation. It's the type of the calling object that's referred to by that variable. The variable is just a reference. We follow the reference, get to the object, and that's what we're interested in, this object. It's of type character. We look in the character class, we find win battle, that's the one that's going to be called. So we're calling this one right here. The parameter is XP. And now we're ready to call the code. This dot battles1 increment, this dot battles1 plus plus, this dot experience points plus equals XP. XP is a separate expression. Start over in the stack frame, 10, 10. And this returns as return type void. Nothing to return, just returns. And then we're ready for the next code. We're going to create a party object. So party, we got another constructor. And again, these arrows, maybe that is something that bugs me a little bit. We're seeing another constructor. Constructors are starting to be familiar to you at this point, I sure hope. New party. Look at the instance variables for party. I have members. I have battles1 equals 0. Members is uninitialized. Technically, it gets the value null. Battles1 equals 0. So if you want to do null here, if you want to really study up on stuff and do null and then cross it out when it's initialized, that's technically what is happening here. I don't expect anybody to do that. I'm not going to do it in my traces. But if you do that, you are more correct than what we're tracing. Just a detail that we don't have to get, in 116 we don't got to get too bogged down on. And then OX400. No parameters, no arguments. And then we're ready to run the constructor, which is going to initialize members. This dot members equals new array list. This dot members equals new array list. So we're creating an array list which has no variables at the moment. And then that array list is being assigned to members, to this dot members equals. So we have a reference in an object's instance variable on the heap. So we have a reference on the heap. This is absolutely allowed. This is something we can do, and it's something we'll see quite a bit, including just in this trace right now. We're going to see this quite a bit. This because spoilers or whatever. But this array list is going to also store references to character objects. So we're going to have references upon references upon references. It's references all the way down when it comes to OP traces. So we have our party and members. It gets new array list. I see the keyword new, so I know I'm clicking the new object button, which I already did here. So we created the object, and we do have a constructor call, and here's good a time as any to give this disclaimer. We don't trace any code that's internal to Java in this class. So I don't expect you to trace through the ArrayList constructor. Technically, there is a new stack frame for ArrayList that goes on the stack, and it executes that code, which we actually did see. This dot element data equals the empty element data array. Like, we did see that. We could trace through it. But if it's internal to Java, we're not going to bother. We didn't trace through any print line calls. We're not going to trace through any like math.absolute value calls. ArrayList, ArrayList.add.get. We're not going to trace through any of those method calls. We just don't trace through them. Same thing in 115. You never trace through anything that was internal to Python. We're not going to trace anything internal to Java. So even though we know that there is a constructor call that goes on the stack, we're not tracing it. Since we're not tracing it, there's no constructor to link here, so we're not going to do any of that. But you do have to know that new array list, there will just be an array list that appears on the heap, and it's tracked by a reference. You just same thing you did in 115 that we did last week. You just have to know that. Even though we know that there is a constructor call at this point, after talking about constructors, we don't trace them for ArrayList or hash map because they're internal to Java. So this constructor is done. I forgot my return arrow. This is done and gives OX400 up here. Okay, let's have a couple add character calls. So we have party.addCharacter. Party is OX400. Oh my goodness. OX400, and there's me thinking ahead. I try not to. I try to turn my brain off a little doing traces. I tried to jump ahead a little bit, and it always bites me. So the parameter is member, so I always recommend just take it slow, one line at a time, and just blindly do what the code's telling you to do. Member is hero. Hero is OX200. And we'll start seeing things like this too. Stack frames where there are no actual values. Well, there are values, but the values are all references. And then add character, it's being called from an object of type party. So we're looking at the party class for an add character. There's only one add character method in this code, so we can't get this one wrong. Is member, and then this.members.add. We're going to start seeing lines like this, and the big one is this one right here that we're headed towards. We're going to start seeing lines like this with multiple dot operators in the same line. This is something where, well, I guess you could have this situation in Java. When you had nested lists, you could. But we're going to see a lot of these in 116. So getting used to tracking references through the code is going to be very important. So we have this, which is OX400. Dot means take me to your object. So we're over here at this party object. And then looking for a variable named members. We find it right here, which resolves to OX500. We hit that with the dot operator. So saying take me to your object again, dot takes us over here to this array list, and then we're calling the add method. So we're calling add on this array list. Add is internal to Java, so we're not tracing it. We just have to know what the add method from an array list does. And what we're adding is member. This is a new expression. For arguments, you can kind of think of this as everything with your PEMDAS rules, everything inside the parentheses is resolved first. Technically, this is resolved before everything I just went through, but I like going left to right. But this is a new expression. So since this is a different expression, it's resolved from the stack frame. So even though the add method is being called from the array list, when we resolve member, member is being resolved back from the stack frame. And member is OX200, so we're adding OX200 to the array list. So we have a new index 0, which is OX200. Uh, we we have interviews in the fall and spring, but it unfortunately has to get cut in the summer just due to time and logistics. There's no way we'd realistically be able to pull it off. So sadly, I like interviews. It's one of my favorite parts of the course too, but unfortunately it doesn't make it in the summer. And then add character resolves. It returns void, which we'll start seeing lots of void methods. Actually, all our methods are void in this example. Lots of void methods moving forward because, well, we're going to be doing a lot of stuff on the stack. Add character. Wow. I think I have this in my clipboard. I'm not going to think. I'm just going to paste it. Again, being called, we're doing add character fighter now. This is the party, OX400 still. And then member is fighter from the main stack frame, which is OX300. And then we're doing the same thing. This dot members dot add. We're calling add member, which is OX300. So at index 1, we're getting OX300. Method call ends. And we're finally ready for the big one, this party.win battle. Win battle, it's being called through the party. So OX400 again. And we have one argument, which is 20. I haven't looked at the method yet, but I know the argument's 20. And then we need to figure out which win battle to call. We're doing party.win battle. So party was OX400. That's the calling object. So the calling object is of type party. We look at the party class and find win battle right here. So this time we're calling this win battle. So knowing that this win battle and this win battle are calling two different methods is important. And the method that's called depends on the type being referred to by the variable's reference. So this is being called through a party. And I see the parameter is XP, which is actually the same parameter in both of them, but just to emphasize the point, I pretend I don't know, you know. So this dot battles 1, increment that, goes up to 1. And then our big one, this big loop, we got 13 minutes to go through this loop. We got this. Timing's looking good. And when we get to this loop, we do have a variable declared as part of the loop, so I do need my code block. I have to have a code block for x, which equals 0, because when this loop ends, that variable is removed from memory, and I'll cross out the code block. So since we have a variable being declared as part of a code block, we need our code block in the memory diagram. So x equals 0. This right here, size, is a method call, but we don't have to trace it because it's internal to Java, but we do have to know what it does. It's this dot members dot size. It's asking this array list for its size, which is 2. It's got 2 elements. So 0 less than 2 is true. We're going to execute the loop. And this beast of a line right here, let's do it. Who's ready? I'm ready. If you're not ready, let me know what your questions are. I'll help you get ready. So this is OX400. Dot means take me to your object. So we go to OX400. Then we're looking for a symbol named members, or variable named members, an instance variable in this case. We find it right here. So this dot members resolves to OX500. And then we're hitting that with the dot operator, which takes us to OX500, which is this array list. So we're at this array list calling the get method. So we're saying, hey, array list, get me something by index. That something is going to be x. And this is a new expression. So we're starting back over at the stack frame for this. We're in the win battle method call. So we're looking for a symbol x. We find it here and it's 0. So when we call get from this array list, we're getting the value at index 0. So it's going to resolve to OX200. So this entire part right here, this entire expression here, resolves to OX200. So all that, this.members.get of x resolves to OX200. And then we hit that with the dot operator. We're bouncing around memory again to jump over to OX200 to this character right here. So now that we're at this character, we're calling a method named winBattle. So from OX200, we're calling winBattle. So let's get what we know on here. We have a new stack frame for another winBattle call. This is OX200. We know that much. And then the argument, this is a new expression, so we're evaluating this from the stack frame. We're still in the winBattle stack frame of the party class. So XP is in this winBattle from the party class, and XP is 20. So I know the argument is going to be 20 in this case. Now, which winBattle is being called? Well, winBattle is being called from OX200, which is of type character. So I'm back in the character class for this winBattle. Parameter is XP. And then I'm ready to actually make the method call. This dot battles1 plus plus. This dot experience points plus equals XP gets us to 30. Then this stack frame ends. That's the end of the loop. Execute our increment statement. X increments to 1. Check our condition again. 1 less than 2 is still true. And we're going to do this big thing again. If you have questions about this line right here, if you understand what this line is doing, you're going to do fine on the OOP, assuming you pay attention to inheritance lectures as well. You're going to be doing fine on the OOP tracing. So if there are questions about this, I want them. I want your questions so I can answer them. This dot members dot get x is 1, so we're going to get the value at index 1, which is OX300, dot winBattle. So we're calling winBattle from OX300 this time. So this is OX300. OX300 is of type character, so we're calling this winBattle method here. We have XP is 20. Then we execute the code in winBattle. This dot battles1 plus plus. This dot experience points plus equals EXP. And that method exits. We get to the end of our loop again. Increment x up to 2. 2 less than 2 is false, so the loop ends. We cross out our code block. X no longer exists. Next line of code is the end of this method call. So the winBattle method call ends. Then we go back, and here we might lose track of things and forget what we're doing. If you ever lose track, where you're currently executing is the first stack frame, starting from the bottom and going up, the first stack frame that's not crossed out. So all these have already been resolved. They're no longer in memory. And we get all the way back to the main method at this point. The main method, we just finished executing party.winBattle of 20. We hit the end of main, cross out main, program's over. This is the final state of what our heap was at the final execution of our program. So we do see that the character that we why do I try to pronounce that name? I never know how to pronounce that word. Colloquially, oh my goodness. That we just kind of know as hero is actually whatever object is at OX200. I gotta practice that word. Colloquially. I gotta stop trying. I'm embarrassed at it. I'm just butchering it. OX200 is this character because we could have multiple references to this object in our program, which in fact we do. We have this hero variable which shows OX200, but also this array list at index 0. So the member the 0th member of the party, like, whatever this means, party dot members of 0 is OX200. There's no indication that this is the hero. That's just one of the names of a variable that happens to be storing a reference to this object. This really is just the character at OX200. That's what this character is. But they did win 2 battles and gain 30 experience. And the other character, which we kind of know as the fighter, is actually just the character at OX300. They've won 1 battle and gained 20 experience points. Kind of what we would expect from looking through this code if you're just skimming through the code. This is how mechanically all that happened. And the big thing is this line right here where we're bouncing around memory. And if you do understand everything that happened here, like this trace is pretty complex. There's a lot of moving pieces with this one. If you can trace this one, aside from, we haven't done inheritance and polymorphism yet, but aside from that, you're going to be solid on the objects and classes portion of the traces. If you could follow this one, I wouldn't give you something quite this complex on a trace. Well, maybe I will, just because it's all the OOP concepts rolled into one trace. It will just naturally grow in complexity. But if you can do this trace at this point in time, you are definitely on track with your traces. But you do actually have to be able to do it. I always see this every semester. Make sure you can actually do a trace like this. Like even this exact trace, after this lecture, after you watch this lecture, going through the tracing tool and just pasting this code, do the same thing I did today. Just paste the code here and go through the entire trace, preferably without referring to the lecture at all. And then once you're done, then go back to the lecture and see if you got the same exact thing I did. See if everything that you did matches everything that we have here. If it does, then you are absolutely solid. You are on track for traces. Keeping up to date with every single subsequent lecture after this one, and you'll be doing absolutely fine in this course. You're going to be passing. You'll have as long as you're good with the problem sets, you'll be getting a good grade as well. You'll be doing fine. If you struggle a little bit with this one, you still might get through, because this one is fairly complex, especially this line, 3 dot operators in the same line, a lot going on. But if you can trace through this one the way I just mentioned, you're doing great. So any questions on any of this? And the reason I worded it like that, because tracing, I mentioned this last time, but tracing is one of those things where it might not seem too hard watching me do a trace. Like, you should be able to follow everything I did without too much struggle. Maybe, a lot of this is pretty new, so maybe even that's a little bit of a struggle right now. But following me doing a trace isn't too hard compared to actually doing the trace yourself. There's just so many little things that you do have to remember all the rules for. But doing this as a practice trace can really give you good practice for those traces. Because I see a lot of students go, oh, I followed lecture fine, I'll be good for the traces, and then don't actually practice. That's not a good way to. It's not a good way to roll. And we do have some practice traces. If you do these traces, I don't think we have the solutions available to you right now for these. I don't know if we will offer them. Oh, that's an answer to chat. I thought you were just saying that you disagree with what I just said. I assume you're answering about the interviews. Or if you're disagreeing with me, let's chat. Let's have a debate. So we have these traces. If you do these traces and then come to office hours with the trace that you did, myself, the TAs will be happy to go through them. Or even ask on Piazza if there's actual demand for, this is the one most relevant to the traces. These two are more of, no, this one's fine too. Number cruncher, I think, is, this is just static methods. So this is more 115. Yeah, answering about the interviews. Yeah. Cool. This is more 115 concept. You should still be able to do this one, but it's a little less important. I can't even say that, because if you can't do this one, you're not going to be able to do any of the other ones. Everything else builds on this. But if you even ask on Piazza, post your trace, we can give you feedback that way too, if you do it as a private post. Where's a public post even? You're not submitting that for a grade. I suppose you could do that as a public post. But anyway, we have options for you, even if we're not just distributing the solutions. That alarm means it's time for me to hop on to office hours. I'll be in office hours if any of y'all have questions. Problem set 0 deadline is in 2 days. Summer goes fast. Have I said that before? Is in 2 days on Thursday. There are quite a few office hours before then. You have all of the office hours. I told the TAs I want the office hours between Tuesday's lecture and Thursday's deadline. So we did put them all in Tuesday, Wednesday, Thursday. I kind of view the summer as a 3-day week. The week is Tuesday to Thursday, and we have 5-day weekends, or 4-day weekend. Wait, is it only 4-day? Yeah, 4-day weekends. I would recommend getting started on the problem sets during that 4-day weekend. But for me and the TAs, it's kind of a 3-day week. We'll still watch Piazza on the other days, but yeah, this deadline's coming up. If you have questions, hit me up in office hours. I'll be in the Zoom meeting as soon as I shut down stream, and then click over to the Zoom meeting. All right, take care, everybody. See you. If I don't see you in office hours, I'll see you on Thursday for linked lists. Take care, everyone.